Hey guys, welcome back to another video. In this video, we're going to look at the calculation of entropy change and the formula for finding Gibbs free energy and calculating whether or not a reaction is feasible. So, in the previous video of this series, I talked about an example where I tried to find out with arbitrary values whether or not this reaction, calcium carbonate decomposing, is feasible. I mean, whether or not the entropy change is negative or positive. So, in that case, we found out that calcium carbonate going from one reactant, that is a solid, to forming two reactants, that is one a solid, one a gas, is actually a process where the entropy increases. That means the energy is far more distributed. That means your system is now more stable due to increased disorder and due to increased distribution of the energy. So, in our case, we found out that del S over here is positive. Therefore, this energy is likely to happen. However, we're going to see that in all cases, in all reactions, your entropy does not need to increase. It might even decrease, resulting in a del S value that is negative, meaning entropy goes from higher to a lower value. So it might go from a liquid or a gas to turning into a solid. And even in those cases, the reaction might be feasible. The reaction might actually take place. So we're going to see how to calculate the entropy changes first, and then going to realize what other ways there are to figure out if a reaction is feasible. Is it going to take place? And is entropy the sole factor determining the feasibility of the reaction? Now, to find out the entropy change of a system, we find out the entropy of the product, final product, and the sum of entropy of the reactant, and then subtract it and see if our entropy change is positive or negative. So first of all, let's look at an example where we're reacting two magnesium, 2 moles of magnesium with 1 mole of oxygen gas forming magnesium oxide. So in this case, what are we doing? We're finding the sum of entropy of our product. What is the product? Magnesium oxide. What is the entropy of magnesium oxide? 38.2. 38.2 times 2 moles of magnesium. That is giving you sum of entropy of the product. Minus entropy of the reactant, that is magnesium. 2 times entropy of magnesium, that is 32.6. Plus entropy of oxygen, which is 205. Now, when you find the difference of the product and reactant, you're going to see your entropy change is negative, minus 193.8. Now, you might argue that since the entropy change is negative, going from a state of increased disorder to decreased disorder means energy is being less stable, less distributed. So the system must be less stable. This reaction shouldn't take place. However, if you go back to your AS level or O level, you might have seen this experiment where reacting magnesium plus oxygen is actually quite spontaneous and is very feasible, meaning it happens in room temperature if you react both of them together. It is very exothermic. It releases a lot of heat to the surrounding. So the system is highly exothermic, right? So this reaction does take place even though the entropy, the change in entropy is negative. The reaction still takes place. Therefore, entropy change is not the sole factor determining whether or not a reaction is feasible. So we have to look at other ways to find out if a reaction is feasible or not. And that leads us to Gibbs free energy. This is a way to find out whether or not a reaction is feasible or not. Now, what is Gibbs free energy? This is a method, or the change in Gibbs free energy actually. The change in Gibbs free energy is a measure of checking the spontaneity of a reaction to see if a reaction is feasible or not. So when you find out the change in Gibbs free energy, that is going to tell you that if that reaction is going to take place or not in, let's say, a certain temperature. If your room temperature is, let's say, 298 Kelvin, at that temperature will the reaction take place. So before getting into the formula, let's first understand what does Gibbs free energy or the free energy term really mean. Now, think of free energy in terms of this. It is the amount of energy, the maximum amount of energy, max amount of energy that is available in the system to carry out the reaction. Therefore, if your system consists of magnesium and oxygen, do they have enough Gibbs free energy to carry out the reaction and form magnesium oxide? So in that case, to find that out, you would have to calculate the Gibbs free energy of the product and the Gibbs free energy of the reactant. You don't need to do this in A2 level, but this is the logic behind it, that the Gibbs free energy of the products need to be less than the Gibbs free energy of your reactant. Therefore, your change in Gibbs free energy needs to be negative. Why is that so? Your reactants need to have more energy such that this energy can do useful work to convert the reactants into products. So let's say your reactants Mg and oxygen had 50 joules of energy. It's just a random number. And this energy, let's say 20 joules of this energy is used up into converting or producing magnesium oxide. So now the Gibbs free energy of MgO is 30 joules. So if you calculate, let's say 50 joules is the sum of Gibbs free energy of the reactant, that is 2 moles of Mg plus 1 mole of O2. So it lost 20 joules of Gibbs free energy in converting from the reactants to the products. So if you plug these value in the equation, you would see the Gibbs free final, that is the Gibbs free energy of the products, is going to be 30 joules minus Gibbs free energy of the reactants. Sum of Gibbs free energy of the reactants is 50 joules. That is going to give you 20 joules, negative 20. That means energy was lost. Where was it lost? In forming the products, in carrying out the reaction. So Gibbs free energy is the energy of the system that is available to do useful work, to convert into the products. Okay, so when the Gibbs free energy is negative, that means the reaction is going to take place. If the Gibbs free energy is positive, that means there's the energy is not enough to carry out the reaction. So if Gibbs free energy is negative, it has energy to perform the reaction. If Gibbs free energy is positive, you need to add extra energy from outside to carry out the reaction. It needs energy from its surrounding to carry out the reaction. It on its own cannot carry out the reaction. It needs added energy. So now let's go to the formula of change in Gibbs free energy. That is given by your change in enthalpy of the system, be it exothermic or be it endothermic. Subtract that with T del S. What does T del S give you? T del S is temperature, that is the unit of it is Kelvin, times the change in entropy, that is the unit of it is Joule per Kelvin per mole. So if we simplify this, the Kelvin and Kelvin cancels out and this gives you Joule per mole. So what does that mean? T del S is giving you the change in energy due to the change in entropy. The change in energy due to change in entropy. So you are subtracting change in enthalpy and change in energy due to the change in entropy. So at the end of the day, what you're getting is there enough Gibbs free energy in the system to carry out this reaction? If your Gibbs free energy is negative, yes, the reaction will take place. If the Gibbs free energy is positive, no, the reaction won't take place because there is not enough free energy in the system. Okay, so let's look at the three cases. When the Gibbs free energy, change in Gibbs free energy is 0, let's say the enthalpy change is 500 joules and the change in energy due to the change in entropy is, let's say, results in minus 500 joules. At the end of the day, in the system, there is the net change in energy is 0. What this means is the rate of forward reaction and rate of backwards reaction is the same. It is in equilibrium. There is nothing happening in the system at that point, since there is no net gradient of the system. What I mean by that is, let's say, in this hand, I have 100 joules of energy. In this hand, I have 0 joules of energy. So if I connect both these hands, the energy is going to flow from this hand to this hand to become more stable. However, in the case where the change in Gibbs free energy is 0, there is no net change in the system, which is why it stays where it is and no reaction takes place. However, if you tip it over a little bit and there is enough Gibbs free energy, the reaction is likely to take place. The reaction is likely to take place, right? So let's say if let's say the enthalpy change, the endothermic process results in 500 joules of energy, it needs 500 joules of energy, and let's say T del S results in 500 joule. If you increase the temperature, it will become, let's say, 600 joules. In that case, you get minus 100 as the change in Gibbs free energy. In that case, the reaction is feasible. That means if you're increasing the temperature in case of an endothermic process, granted your change in entropy is positive, you can make the reaction more feasible. We will look into these factors in details later on, how to increase the feasibility of a reaction. So yeah, so when changing Gibbs free energy is 0, equilibrium, nothing happens. When changing Gibbs free energy is negative, the reaction is feasible. The reaction is likely to take place. When the change in Gibbs free energy is positive, the reaction won't take place, right? These are the three cases. If we look at an example, calcium carbonate again, going into calcium oxide and carbon dioxide. So the enthalpy change, let's say, over here is given 178 kilojoule per mole. Note one thing, entropy change values are given in terms of joule and enthalpy change values are given in terms of kilojoules. Do convert all of them in one unit. Let's say if you convert everything into joules, convert kilojoule into joule. If you convert everything into kilojoule, convert joule into kilojoules as well. Okay, so if we calculate for this, what is the enthalpy change of the system? This, 178 kilojoule per mole. What is the change in the energy change due to change in entropy? Multiply 298 with the change in entropy, which is 159. But you need to convert this into kilojoules, so 10 to the power minus 3. So now you have the change in energy due to change in entropy. Plug that in over here, and what you're going to see is the Gibbs free energy is actually positive. What does this mean? This means the reaction is not going to happen at this temperature. Is the reaction going to take place? No, since it is positive. What can you do though? Over here, what you can do is you can increase the temperature. So let's say if I increase from 298 to, let's say, 400 kelvins, that would result in a negative value. If you want to check it out, let's check it out. 400 times 159 into 10 to the power minus 3. That results in 63. Okay, so we need to increase it even more. Let's say 2000 2000 kelvins. If we use 2000 kelvins, what happens? 2000 times 159 into 10 to the power minus 3. That results in 318. So 178 minus 318. That results in minus 148 kilojoule per mole. So if you use 2000 kelvins, in that case, what happens is this part of the expression becomes more negative, which is why at the end of the day, your answer is, your change in Gibbs free energy is minus 148. That means if you increase the temperature in this case, the reaction will be more feasible. The forward reaction is favored, right? The forward reaction is favored. So, this is your change in Gibbs free energy. Now, I just gave you an example of how temperature is affecting your Gibbs free energy and how temperature is affecting your feasibility of the reaction. So if you look at a few cases, there are 4 cases where the temperature is going to affect your feasibility of the reaction. The first case, or the first part of the case, is for exothermic reactions. So in case of exothermic reactions, your change in enthalpy is negative. Change in enthalpy is negative, right? Energy is taken out of the system. So this part of the expression, mind you, is negative. Del H is negative. So your entropy can be either positive or negative. So let's take that into account. If del S is positive, what happens? If your del S is positive, that is, this value is positive, that means negative minus a positive value, that will result in negative minus negative. So whatever your temperature is, your ultimate value will always be negative. Because let's say your temperature is really small, 0.0001 Kelvin. Even in that case, since your enthalpy change is negative, your change in Gibbs free energy will ultimately be negative as well. So let's say your temperature is infinitely high, let's say 200,000 Kelvin. What's going to happen? Even in that case, since minus and positive will give you a minus value, your change in Gibbs free energy will also be negative. Therefore, with increase in temperature, if your change in entropy is positive and change in enthalpy is negative, in that case, as you increase the temperature, reaction becomes more feasible. Therefore, forward reaction is faster. Rate of forward reaction is faster. Okay, so either way, the reaction will always be feasible since change in Gibbs free energy is always negative, right? So in case of exothermic reaction, if your change in entropy is positive, it's always feasible. Next case, if it is exothermic, but your change in entropy is negative, what happens in that case? So, if your change in entropy is negative, this part of the value is negative. Therefore, you have a negative in front, negative value minus a negative value. What that results in is negative plus positive. So what this means is, let's say your temperature is 2 kelvins, right? 2 times, let's say your change in entropy is 20 minus, let's say your change in enthalpy is 200, right? Sorry, it's going to be plus. It's going to be plus. So let's say your change in enthalpy is minus 200 plus 2 into 20. This is your exothermic part and this is your change in entropy. Now what you can observe over here is since the temperature is really low, your ultimate value will be 2 times 20, 40. So ultimate value is 160 joules. However, if you increase the temperature to let's say 100 or let's say 120 or 200, what do you get? You're going to get the answer to be minus 200 plus 2 times 2 is 4,000. And your ultimate answer is going to be positive 1800. Positive 1800 is the change in Gibbs free energy. Therefore, if you increase the temperature, the reaction becomes less feasible. So, if you increase the temperature, the reaction becomes less feasible. Therefore, negative plus T del S, if you increase the temperature, less feasible, right? Because it becomes more positive. With increase in temperature, del G becomes more positive, hence less feasible. Therefore, for low temperature, reaction is feasible. So these are your two cases in case of exothermic reactions. Now, let's further look into endothermic reactions. What happens then? If you have an endothermic reaction, that means your change in enthalpy is positive. Let's say positive 500, right? And you have minus T del S. Let's say your change in enthalpy is positive due to the endothermic reaction, and your entropy, change in entropy is also positive. That means positive minus positive, right? It results in positive minus positive. So, if you increase your temperature, what do you think is going to happen? If you increase your temperature, your ultimate value will be more negative. So, if you look at an example, positive 500 minus, let's say, 2 Kelvin times change in entropy is 30, you're going to get 500 minus 60, right? So it's going to be 440. 440 joule is the change in Gibbs free energy. This is positive, so not feasible. However, if you increase the temperature to, let's say, 200, it's going to be 200 times 30 is 6,000. So 500 minus 6,000, this is going to give you 5,500, negative 5,500. So as you increase the temperature to 200 Kelvin, the reaction became, the reaction now has a negative change in Gibbs free energy. Therefore, as you increase the temperature, in case of a positive entropy value with an endothermic reaction, your reaction becomes more feasible. With increase in temperature, del G becomes more negative, hence more feasible, right? So at low temperature, del G may be positive, hence less feasible. So in case of endothermic reaction, what are you going to do? If your entropy, change in entropy is positive, increase the temperature. And that actually matches with our, previous cases where we used to solve the paper, where if you had an endothermic, if your forward reaction was endo, increasing the temperature resulted in a faster forward reaction. So if your forward reaction is endothermic and you increase the temperature, what usually happens is the rate of forward reaction increases. This is the reason why it happens. Right? If we look at another case where the change in entropy, let's say, is negative. However, your enthalpy change is positive. So enthalpy change is positive and minus, and your entropy change is negative. Positive plus positive. Now, what happens over here is whatever you do, nothing is going to change your Gibbs free energy. Nothing is going to change the sign of your change in Gibbs free energy. Why is that the case? Because positive plus positive will always give you a positive value. So no matter how you change the temperature, your ultimate change in Gibbs free energy will never be negative. Therefore, if your change in entropy is negative and it is also an endothermic reaction, it will always be not feasible. So these reactions are never feasible and these reactions will not take place. So if del S is negative and if del S is negative with an endothermic reaction, del G is always positive, hence never feasible, regardless of the temperature. Now, this is your Gibbs free energy and feasibility of a reaction, right? So we learned how to how to calculate change in entropy, how to find change in Gibbs free energy, what is Gibbs free energy, and how temperature affects change in Gibbs free energy, or how temperature affects the feasibility of a reaction. Now, this is actually the end of the chapter entropy, and in the next video, if you're interested, I'll explain how the change in Gibbs free energy formula is derived, right? So yeah, see you in the next video.